Thank you for the introduction. Welcome everyone to my presentation. I'm going to talk about a framework which allows to analyze a signal processing task in order to find a suitable configuration which then can be implemented on a microprocessor. The motivation in our group is that we are working with body sensors. A body sensor is a small compact sensor module which you can attach to the body to record vital parameters. And currently our body sensor includes a sensor for ECG, breathing, temperature, and body acceleration. And all the signal processing is done on a Texas Instruments microcontroller, MSP430. The problem is that we are already doing quite a lot of signal processing tasks on that microprocessor to calculate the heart rate, the breathing rate, the activity profile, the body orientation, and the velocity of the person. And this is all done in parallel. So an efficient signal processing is very important. The signal processing has to be done in real time, and it has to assure that the body sensor runs for a long time. So it has to be energy efficient. And then the goal of this work was now to create a framework which allows to automatically analyze a signal processing task to perform a design space exploration of that task in order to find a good combination which can then be implemented on the microprocessor. As a signal processing task, we are looking at an embedded classification algorithm in this case. An embedded classification algorithm consists of a feature extraction step and a classifier. And it can be configured with lots of parameters which then influence the accuracy and the runtime behavior of that algorithm. And our framework helps to analyze this. Furthermore, we can analyze which configurations, which source code implementation and assembler optimizations or compiler optimizations are useful for implementing it. And we can as well simulate a whole hardware platform by including an instruction set simulator of a microprocessor. Then in the end, our framework points out the Pareto-Optimal configurations for that algorithm. The Pareto-Optimal configuration in terms of accuracy cannot be further improved in terms of accuracy without increasing the amount of clock cycles which are required for that algorithm. This is the flow of our steps of our framework. It starts with a parameterization where we input the user's specification. You can decide which features you want to analyze, which classifier, which target microprocessor is going to be analyzed, and which data is used for that. Then, as we are using classification algorithm, we have to split our data into a training and an independent testing data set. And then ongoing, the training of the classifier is done. We have implemented now two basic classifiers, an artificial neural network and a decision tree. And after the training process, we then transfer the configuration into the microprocessor code. For example, in case of the artificial neural network, that could be the weights of the neurons. Then this microprocessor code is compiled and is executed using an instruction set simulator of the target microprocessor platform in order to determine the amount of clock cycle it requires and the accuracy of that configuration. The results of the frameworks are then statistics on the classification, as I said, accuracies, clock cycles, energy estimations, the Pareto-Optimal configurations. For our framework, we have chosen at the moment a microprocessor which was developed in our group. It's called the Corva ULP. It's a 32-bit microprocessor with a VLIW architecture, and all the functional units of that microprocessor can be specified during design time. We also have an ultra-low power ASIC realization of that microprocessor, and the goal is to use that in future to replace the MSP430 on our body sensor prototype. And we use it therefore in our simulation here. But our framework supports other microprocessors as well. Then as a classification algorithm, we have chosen a velocity estimation. It estimates the velocity using the acceleration sensor on the body sensor module. And in the figure, you can see stride patterns of a person walking and running on a treadmill and see the variations which occur due to the different velocities. This velocity estimation uses several functions of our signal processing library. For example, the peak-to-peak amplitude, the variance, and the root mean square from the acceleration signal. All these feature extraction steps are done in fixed point operations because that is way faster on a microprocessor. We're also using the two classifiers, the artificial neural network and the decision tree. The artificial neural network is based on only integer operations, and we've approximated the activation function here using 6 points to speed up the execution. In the design space exploration, we asked ourselves, what sampling frequency do I need in order to estimate the velocity? How many axes of the acceleration sensor are necessary? And which features are the most important one? How many hidden neurons does the artificial neural network need? And which parameters are best for the decision tree and training process? In total, we had 1,008 simulations, and we parallelized our simulations, spreading them on 30 threads, which were then run on 12 computers. It still took about 10 hours to do that. Just to mention the data we've used for our simulations, we collected in our gym at the University of Bielefeld using 22 subjects and our body sensor. I want to now get into the results of the exploration. In that figure, you can see the 1,008 different configurations in terms of accuracy and cycle count. And the Pareto-Optimal configurations are circled, and they form the Pareto front. And in this case, we have colored the sampling frequency to show the impact. So a sampling frequency of 18 Hertz is the green area. You can achieve about 93.5% accuracy just using 18 Hertz sampling frequency for the acceleration signals. For the maximum accuracy, down here, we needed 75 Hertz. So we can reduce the sampling frequency in order to save clock cycles. Then we looked at the different feature combinations we used. Our most important feature for estimating the velocity was the variance, that is C1, it's the orange one. This feature, taken by its own, achieved over 93% accuracy. Our fastest feature was the amplitude feature, it's at the top left, but it's also the one which had a little less accuracy. For the full accuracy, we needed a full feature space combining all our three elementary features, C1, 2, C3. Then the big question, which classifier do I use? For this scenario, the decision tree is definitely faster for an accuracy up to 92%, but then the artificial neural network showed to be more efficient in terms of clock cycle amount, except for one decision tree configuration here. Our configuration with the highest accuracy, the artificial network, required 10 hidden neurons. So we tried up to 30 neurons, but 10 were sufficient for that task. And the number of hidden neurons are actually a good point to save lots of clock cycles. In this table, I've listed the Pareto configurations again. And if I now would implement one, I would choose configuration 10. It is based on the decision tree, which requires 1,117 clock cycles, and 92% accuracy can be achieved. The next higher, configuration P9, the accuracy is very similar, but the artificial neural network needs 3 times more clock cycles. I want to summarize our work. I've presented a framework which allows to automatically analyze the design space of a given embedded classification algorithm in order to find Pareto-optimal configurations, which then can be transferred on the microprocessor. You can choose from the configurations then what is suitable. We have simulated various parameters, and our framework is very flexible because you can extend it using new features, inserting a new classifier, or even exchanging the instruction set simulator of the microprocessor, and therefore simulating a completely new hardware platform with some functional units like a hardware multiplier. For the design space exploration which was carried out here, we found that 75 Hertz sampling frequency are sufficient and 10 hidden neurons to achieve the highest accuracy. However, if your application allows to reduce the accuracy, let's say on 1.8%, then you can choose configuration 10 and save 20 times of the clock cycle amount, which will then increase your battery lifetime of the sensor node. In our future work, we want to evaluate more algorithms of the body sensor and also look into the instruction level parallelism of the VLIW architecture in order to increase the energy efficiency on the hardware level aspect. Thank you for your attention. Any questions?